Did you hear news? They're shutting down the school because of COVID. So we won't be seeing each other anymore. We have to work remotely. So how the hell are we going to finish this project?
In a crisis for sustainable living, there's a need for affordable and clean energy. For example, Chile currently imports a large majority of energy from fossil fuels. Urban communities in Chile tend to have over 93% of electrification, whereas rural and off-grid communities have a smaller percentage in electrification due to financial barriers for local communities and homemakers. There's a lot of potential for solar energy projects in Chile, but these systems are often too costly, fail, or are not entirely accurate.
For this project, our users are residents living in off-grid rural communities. These residents need space heating, air conditioning, and power for appliance needs. The way these needs are met now typically require the use of energy sources with high carbon footprint and are very costly. Our project is to tackle this issue twofold. One, to find a more cost-friendly way for families to generate electricity and heat for their residential and local uses, and two, to find a way to adapt our solution in different communities with varying needs and stakeholders.
In order to ensure that our project is successful, it is necessary that it meets a set of requirements. For one, it must be cost-effective. We estimated that to be around $2 per watts, which is about the price of a solar panel that's currently on the market, and we aim to make it cheaper than that. Our second requirement is that we want to be able to generate at
700 watt-hours per day,
which with some research we found is enough to power small electronics as well as a refrigerator and even a few light bulbs. Thirdly, we want to be able to recover 60% of the heat that is produced from the system and make use of it. Our last requirement is that we want to concentrate 80% of the incident rays. Concentrators have existed in the past, but we want to be able to replicate their performance by using cheap materials that are readily available.
A trade study showed that the systems that exist with similar functions either do not maximize electrical output, are expensive, or cannot provide electrical and heating needs. Thus, we found a gap for a low-cost cogeneration solution. We had design iterations to think of different methods of concentration, tracking, and have electrical and heating outputs. Our final outcome of each part of the project is the following.
The primary design challenge was to develop a cost-effective geometry that could concentrate rays from the sun onto our receiver. We opted for a design that utilized the point focus so that the majority of the reflected rays would be concentrated onto the solar cell area. The first thing we did was deconstruct a conventional collector so that high cost points, such as a mirror, would be replaced with a luminized mylar, which has a reflectivity of over 90%. However, mylar is a polymer film with little to no structural support, which would be another high cost metric. Thus, we decided on adopting an inflated design in order to keep the overall cost low while minimizing the need for any external structure. Our first design was based on a large beach ball and was spherical in shape. However, this turned out to be very difficult to manufacture, primarily due to the quality of the bonding at the seam between the mylar and the ball itself. The second design was similar to the ball, except that the inflated envelope was a cylinder rather than a sphere. However, this design also turned out to be quite difficult to manufacture. Our third design was based on a revolved compound parabolic concentrator, which attains the maximum geometric concentration for a given aperture. By discretizing the sides and modifying the outlet, we were able to design a square polygonal theta in, theta out transformer, which is very similar to a CPC and is quite easy to manufacture. It also features a high acceptance angle and has a high transmittance efficiency. Based on our testing and simulations, a cost optimization method was conducted to allow us to have the lowest cost design while still having the highest concentration ratio achievable.
The electrical output of our system comes from a solar cell. We chose a SunPower Maxion single junction cell as it was relatively cheap and had very good efficiency. It's worth noting, however, that this efficiency, as with all cell ratings, is rated under one sun, and our system is meant to operate under multiple. Due to the extreme circumstances outside with this pandemic going on, we weren't able to actually test our cell directly and had to resort to simulations. In these simulations, we tested our cell under multiple suns to represent the fluctuation in the mirror, as it's not expected to be perfect, as well as multiple temperatures because likewise, the cooling system is not expected to be perfect. From these simulations, we have a theoretical lowest efficiency of 14% and a highest efficiency of 16%. The drop in efficiency is due to the internal resistance of the cell, which has increasing power loss from the increasing current from the multiple suns. Still though, 14% of 20 is a lot more than 20% of 1, and this cell will produce much more power than a single cell would on its own.
There's a substantial amount of thermal losses coming from the solar cell, so the heat design aims to cool the cell to have it operate at normal temperatures, as well as recover the heat for something useful. The initial design of the heat exchanger features the cell connected to a copper plate connected to an acrylic slab, which would have channels for water to run through in order to cool down. However, for manufacturing purposes, we decided to go for aluminum heat sinks instead of the acrylic. These 3 layers would be sandwiched into an ABS frame for 3 reasons. 1, this would allow for insulation so no external heat losses would occur. 2, the mylar balloon would be able to be connected through the ABS frame in an airtight seal. And so 3, this would allow for inflation of the device itself while being connected to the heat exchanger overall. Now, the amount of heat needed to be covered depends on our needs, so depending on space heating or boiling water. So based on these needs, the volumetric flow rate of the pump can be determined, and this was verified using our Simulink model. We then modeled the flow of the water through the heat exchanger using SolidWorks Flow Simulator and confirmed that it recovered 86% of the heat from the solar cell. And this can be used in a variety of different ways, for radiative floor heating, to be connected to your house for warm showers.
Our latest design iteration has an acceptance angle of 24 degrees. This means less adjustments are required during the day, so it can be done manually by the user. We decided to use a pinhole sun finder for our tracking purposes. In this simple system, there are 2 plates placed parallel toward each other at a distance. A pinhole is drilled on one of the plates, allowing the light to pass through it. If the 2 plates are pointing toward the location of the sun in the sky, only then the light passing through will project a similarly sized circle of light on the second plate. Since the sun finder is connected to our concentrated on the tripod's 3-way head can be used to calibrate the sun finder, thus ensuring that our concentrator is pointing toward the sun at all times.
The final solar floatie configuration has the following specifications. It meets our main requirements and is designed to be modular and adaptable for one's needs.
Our original focus was regional, with most of our research based on the Atacama region in northern Chile. Our aim was to situate our project in Chilean off-grid communities, but we realized that without the means to conduct primary ethnographic research, we cannot ensure that our tech was community-centric and attuned to the needs of each community. This issue risks us homogenizing the needs of vulnerable communities, and so we wanted to find a method of implementation that allows technologies to be adaptable to the specific needs of each community. This was when we realized that we had to reestablish our project compass to ensure that we were still headed in our main guiding direction, which was equitable social impact for the communities that would want to use our technology. We recentered with a holistic view of sustainability, accounting for economics, and environmental and social cultural dimensions. This approach promotes equitable practices and systems that prioritize the end user and their right to develop the products or technologies being implemented in their communities according to their needs and the needs of their local environment, both ecological and cultural.
The key drivers of our research were incorporating local knowledge into the implementation of the project and accounting for various dimensions of sustainability. The idea of shifting our framework to an open innovation model, which is a methodology for engaging and directing external resources to find solutions for specific business opportunities and challenges, emerged as we gained the understanding that social impact is best facilitated through participatory, inclusionary, and user-first means. Through open innovation, the process of development and customization of our tech is effectively opened up to the local community, so they can further develop it for their specific needs. For the development of this project, the most important part is how the open source model helps us incorporate the Sustainable Development Goals into the implementation process, which elevates the impact potential of our project given the international communicative potential of the SDGs. Our final framework, therefore, focuses primarily on access and sustainability, and utilizes the principles of open innovation and the premise of the Sustainable Development Goals to ensure adaptable implementation of our tech.
The first section of our framework deals with community characteristics, and this involves the different geographic, economic, and institutional characteristics of each community. but also deals with their own specific individual needs. This helps us determine what kind of implementation challenges we might face. So for example, the technology needs to be able to meet the different community standards present within its legal framework. It also helps us determine the specific needs of each community and whether the technology adequately addresses them. So for example, each community could have different energy needs, and each stakeholder group could also have different energy needs. In the next section, we deal with the talent that is present within the community. As open innovation projects are characterized by teams with mixed skill sets, we've determined that a multidisciplinary team, such as our own Capstone team, would be the best suited for this project. As a result, the technical and sociocultural knowledge is needed for implementation, and different stakeholders could be engineers, government officials, environmental experts, schools, and even the homeowners themselves. In terms of IP ownership and transparency, our framework outlines that it should be defined at an early stage how new jointly created IP is owned and how its legal rights should be maintained. The free flow of information and transparency in regards to IP should be established between participants at an early stage. The technology also needs to meet a standard of addressing a minimum of 3 sustainable development goals. In order to facilitate open innovation, a large variety of stakeholders need to be involved in the implementation and development process. However, end users should always be the main influencers and should influence, if not all, most of the innovation processes. This is because the technology is being implemented for end users and will most directly affect their lives. We've decided that their needs should be emphasized first in guiding the development and implementation process.
The governance section of our framework outlines that local leadership should be the facilitators or initiators in an organizational capacity, as these parties likely have the resources to fund and organize projects like these. End users, however, should remain the key decision makers, and all stakeholders should be informed of all the decisions that are made in the process. Finally, our last section outlines that our technology could potentially address many different SDGs, depending on the needs of the community and what they will use the technology for. For evaluation purposes, successful implementation of the project would be evaluated based on how well the technology is used to address the SDGs, and it would use an SDG check tool for this purpose. This tool is used to identify potential sustainability effects, including risks and opportunities of an innovation, by estimating whether the innovation has positive or negative potential, using a 7-step scale that ranges from -3 to +3.